This is Unit 10B, Part 3, and we'll be talking about Taylor series. So we have learned to find a Taylor polynomial for a function f. That's what we did in Part 1. Today we're going to extend our knowledge of Taylor polynomials to find a Taylor series for a function. So let's begin. The Taylor series centered at x equal to c is given by, and all of this should look pretty familiar, f of c, f prime of c, multiplied by x minus c to the first power, all divided by 1 factorial, and so forth. And you can see the nth term right here, and that's what's included in this series. So what are we doing? We're finding a function that is equal to this series, okay? It's important to note, again, that if c is equal to 0, the series is called a Maclaurin series. Let's give one a try. Find a Taylor series for f of x equals e to the 5x, centered at c equal to 2, and give the first four non-zero terms, and also the general term. So we're not given any function values or values at derivatives, so we're just going to right away start f of x equals e to the 5x. And let's go ahead and grab some of these derivatives. 5e to the 5x, 5 squared e to the 5x, five cubed e to the 5x. So it looks like we will be able to come up with the first four non-zero terms with just those. And let's go ahead and evaluate each of those. So f at 2 at our center, so that's e to the 10th. And then f prime of 2, that's 5e to the 10th. F double at 2, 5 squared e to the 10th power. And f triple at 2 is 5 cubed e to the 10th. Okay, so now let's go ahead and come up with this Taylor series. And we can go ahead and write that e to the 5x is equal to, it's pretty powerful, e to the 10th plus 5e to the 10th times x minus 2 plus 25e to the 10th divided by 2 factorial, x minus 2 squared, plus, here's our fourth non-zero term, 125. And we could have written 5 to a power here. I almost like that better. Plus 5 cubed e to the 10th, x minus 2 cubed, all over 3 factorial. Now what we'll do is put dot, 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 and we will actually write the nth term here, okay? And so let's talk about what that nth term would look like just by using a pattern. Plus 5 to the nth power, e to the 10th, x minus 2 to the nth power, all over n factorial. So just using a pattern, what we see looks pretty good there. Okay? So Now, we'll go ahead and say that this is equal to the series n equal 1 to infinity of 5 to the n e to the 10th x minus 2 to the nth power, all divided by n factorial. Pretty cool. Okay, there are 3 special Maclaurin series that you must know, and all students must know these. And these are the series for e to the x, sine of x, and cosine of x. So we're going to derive a series for e to the x. And take a look at this. So f of x, to bring this over there and this along here, okay? So we have f of x is equal to e to the x, f prime of x is equal to e to the x, f double prime is equal to e to the x, and so on and so forth. So if it's a Maclaurin series, we know c is 0. So f of 0 is 1, f prime of 0 is 1, f double prime of 0 is 1, and so forth. So what we're doing here is we're going to derive a formula. These series, we're going to derive an infinite series. So what we would have here would be 1 plus, of course, 1 times x. We can put that over 1 factorial, plus 1 times x squared over 2 factorial, plus 1 times x cubed over 3 factorial, and so on and so forth. So, what do we see? For what values of x does e to the x equal the series that you found? We could write this as 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, 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 plus, what do you notice, x to the n over n factorial. And this is for any x value between positive and negative infinity. So we could write this as the sum of the series, n equal 1 to infinity, and we would have x to the n over n factorial. Now that looks like we might want to go ahead and start this one at 0, and that might have been this case here if we would start this one at 0, okay? Because anything to the 0 power is 1, and we would just end up with e to the 10th, yes. Okay? Well, that works out nicely. So, to derive a series for the sine of x, we were going to do the same thing. F of x equals the sine of x. F double. F triple. And you can see that it's going to cycle. Now, if this is a Maclaurin series, of course, c is 0. And I think they might have said that in this this note here, that all of these are Maclaurin series for e to the x for the sine of x. So f of 0, f prime of 0, f double of 0, f triple of 0. And as you can see, we will have 0 here, 1, 0, -1. And you can see that also alternating, okay? So let's go ahead and write a few of those terms. The sine of x is equal to, And now we're going to have our first term, which is 0 plus 1 times x divided by 1 factorial plus 0. And then we have a minus 1 times x divided by 3 factorial plus, and you can see that's going to be a 0 plus dot, dot, dot. It's going to keep going. So let's see if we can go ahead and write this series that we just found. It's just going to be x minus x over 3 factorial, you guessed it, plus x cubed over, whoops, I think this was supposed to be an x cubed over 3 factorial, and you guessed it, x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot, 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 plus. Now let's take a look at this. We're going to have an alternating negative, positive, negative, starting with positive, x to the 2n plus 1 divided by 2n plus 1 factorial. So 2n plus 1 allows us to start with n equal to 0, okay? And then we have negative 1 to the n, x to the 2n plus 1, all divided by 2n plus 1 factorial, okay? And now also the sign of x, this is for any x value between negative infinity and positive infinity, okay? So the next one that we're going to look at is the cosine of x. So let's start with f of x equals the cosine of x. F prime is negative sine of x. F double is negative cosine of x. F triple is going to be the sine of x, and so on and so forth. Since this is Maclaurin, we're going to have c equal to 0. So f of 0 is 1. F prime of 0 is 0. F double is a negative 1. F triple is a 0, and so on and so forth. So let's see what we have here. We're going to say here that the cosine of x is equal to, remember we always grab that first term right there, f at the center. That's what we did here when we grabbed that 0. 1 plus 0x divided by x factorial minus x squared over 2 factorial plus 0x cubed over 3 factorial and, whoops, that would be the 4th. Oh, yeah, 3. And then we would have plus x to the 4th over 4 factorial. And you can see what's going to happen because this is your n equal to 0, n equal to 1, n equal to 2, n equal to 3. This is where we left off, but we could see a pattern, okay? So we could actually say that that's equal to, well, let's go ahead and write it down here first. So we have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot, 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 plus, and as you can see, we're going to have negative 1 alternate, x to the 2n. When all of them are even, we'll use 2n. When we have odd powers, we'll use 2n plus 1. okay? All divided by 2n factorial. And again, this is for all x values between negative infinity and positive at infinity. So now, why did I just derive all of this? Because, and let me go ahead and write what this is equal to. This is equal to n equals 0 to infinity. And we have negative 1 to the n. And would that first one be positive? Yes. And then we have x to the 2n all over 2n factorial. And I was just thinking that when n is 0, yes, that works. Okay. So we can manipulate these three very, very special series. We can manipulate them. Or any series we are given to find other series by using the techniques. And we're going to call these manipulation techniques. And here they are. The first thing is that you can substitute into the series. You can multiply or divide the series by a constant and or a variable. You can add and subtract the two series. And guess what? You can differentiate or integrate the series. So we are going to be looking for some patterns. Okay. So find a Maclaurin series for f of x equals the sine of x squared. Give the first four non-zero terms, but then also give the general term. Okay? So what are we going to do here? We're going to substitute x squared for x into our sine of x Maclaurin series. Okay, and let's recall what that was. Here's our sine of x right here. Okay, so let's go ahead, and we could always write that down first right above. We could do that. We know that the sine of x is equal to, and sine is an odd function, so that might help you remember, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus ... Okay? And then we might as well just finish that. Plus negative 1 to the nth power x to the 2n plus 1 all over 2n plus 1 factorial. Okay? So what are we going to do? Everywhere there's an x, we're going to put an x squared. So let's give that a try. So we have the sine of x squared is equal to, well, x squared minus x to the 6th over 3 factorial plus, you guessed it, x to the 10th over 5 factorial minus x to the 14th over 7 factorial. Now, let's go ahead and write that general term. So we're going to have negative 1 to the nth. Now be careful, we're going to have x squared raised to the 2n plus 1 power, all divided by 2n plus 1 factorial. Let's simplify this. X squared minus x to the 6th over 3 factorial, x to the 10th over 5 factorial, minus x to the 14th over 7 factorial, plus ... And we have negative 1 to the n and x to the 4n plus 2 power, all over 2n plus 1 factorial. Isn't that something? And that is the first 4 non-zero terms and the general term. Okay. Use your answer in A to find a Maclaurin series for f prime of x. Well, all we would have to do is, this is the same question. So our f of x is the sine of x squared. So we want f prime of x, okay? So f prime of x would just be equal to the derivative here. So we would have 2x, and this would be minus 6x to the 5th over 3 factorial plus 10x to the 9th over 5 factorial minus 14x to the 13th over 7 factorial plus dot, dot, dot. Now we are actually going to find the derivative of this nth term. Use what we've done before, that negative 1 to the nth. Just keep it there. It's just a constant, okay? Then we're going to bring the 4n plus 2 to the front, x raised to the 4n plus 1. Multiply and subtract, all divided by 2n plus 1 factorial. So you're only taking, remember, these are constants, so they go along for the ride. So you're just doing the power rule on that term. Isn't that neat? Okay, so now let's look at this example. Find a Maclaurin series for f of x equals x cosine x. Give the first 4 non-zero terms and the general term. Well, we already have the cosine of x. So we are going to multiply the Maclaurin series for cosine of x by x. That's all we're going to do. So remember that the cosine of x was 1 minus x squared over 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. We'll write our nth term. Now, what are we going to do? We are going to multiply everything by x. So, think about this. X times all of that and x times all of that. Let's see what we have. X cosine x is equal to x minus, you guessed it, x cubed over 2 factorial plus x to the 5th over 4 factorial minus x to the 7th over 6 factorial plus dot, 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 plus, here we go, negative 1 to the 2n. The only term that's affected is this one right here. We're going to add exponents. So this would be x, x to the 2n plus 1 all over 2n factorial. And of course, this would go on and on and on, just like all of these. We have never really stopped, okay? Even up here, okay? When we get to these terms, that's just the nth term, but there's more terms after that, okay? Okay, one more. Use your answer in A. So we're still back up here at A, right here. Sine of x squared, and we are going to find a Maclaurin series for the integral from 0 to x of that f of x, okay? Again, we're going to give the first 4 non-zero terms, and then, of course, the general term, okay? So let's go ahead and see what we have. In that problem, we had the integral, or we want the integral from 0 to x of f of t dt. And what we came up with in part A was the integral, let me just put that there. F of t, instead of x, we're going to use a t. We had t minus x cubed over 2 factorial plus x to the 5th over 4 factorial. Whoops. I'm supposed to be in t's. Okay. So we had t minus t cubed over 2 factorial plus t to the 5th over 4 factorial minus t to the 7th over 6 factorial plus dot 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 plus negative 1 to the n t to the 2n plus 1 all divided by 2n factorial plus dot dot dot, and then of course we have this dt. Okay, so we're using our answer to A. So if you're going to look up here, just in case you didn't see that, this is our answer to part A right here. And we are using that answer to find this integral, okay? So let's go ahead and integrate. What do? When we integrate, we add 1 and divide. So we have 1/2 t squared, I'm going to need a bracket here, minus, and that 2 factorial stays in the denominator, okay? So we have 1/4 t to the 4th. So I have t to the 4th and 1/4 of it plus add 1 and divide minus add 1 and divide. Okay, let's do the same thing. Don't worry about these terms. We're not using those for integration. The constants just go along for the ride. And let me put that right over here, 2n factorial. And now I'm going to add 1, and I'm going to divide by that. Okay? Plus dot, dot, dot. And I'm going to evaluate that from 0 to x. Okay? So here we have 1/2 x squared minus x to the 4th over 4 times 2 factorial plus x to the 6th divided by 6 times 4 factorial minus x to the 8th all over 8 times 6 factorial plus dot, dot, dot plus negative 1 to the n. We have x to the 2n plus 2 all divided by 2n plus 2 multiplied by 2n factorial. And now you can see how we can manipulate these Maclaurin series to find other Maclaurin series. And that